Assalamu alaikum. Today on 14 February 2021, I'm starting lecture number 2 for week number 15, and the topic of my lecture is induction motors. What we will study in induction motors? We will start with the starting principle of induction motors. Then we will discuss the relative motion theory that is being used for the starting of induction motors. Afterwards, we will consider or try to understand two different types of induction motors that are being used. And finally, we will discuss the equivalent model of induction motors. So these are the topics that inshallah we will cover in this lecture. So starting from the introduction of induction motors, as discussed in chapter 4, there are two types of induction motors. Two types of AC machines. Number one, the synchronous machines, and number two, the induction machines. What was the principal difference between synchronous machines and induction machines? The principal difference was that in synchronous machines, field current was provided by a separate DC power source, while in induction machines, this field current is being provided by a magnetic induction phenomena by means of magnetic induction, or what we can say by means of transformer action, we provide the DC field current. So now what happens in an induction motor, that the stator of the induction motor is just like the stator of the synchronous motor. There is nothing that is different from the stator of synchronous motor. So both machines are having the same stator, and what we provide in the stator, we provide three-phase set of windings. Why? Because for the starting of three-phase machines, we have to provide three-phase set of voltages to the stator winding. So the stator is wounded with a three-phase winding. Now coming to the rotor side. In induction motors, the rotor consists In induction motors, the rotor either consists of a cage known as the squirrel cage, or it is consisting of a dedicated separate three-phase winding. So in both cases, what happens that to start an induction motor, first of all, we provide three-phase set of voltages to the stator's three-phase winding. Due to this three-phase set of voltages that are equal in magnitude, differed by 120-degree phase angle, a rotational magnetic field is produced. So when we provide the stator with a three-phase voltage, what happens that stator produces a rotational magnetic field. This rotational magnetic field rotates about the shaft of the motor, or what we can say, this magnetic field rotates around the rotor of the machine. Now, rotor of the machine is obviously a ferromagnetic material. It's a metal. So what happens that when a magnetic field rotates about the rotor, according to Faraday's law of electromagnetic induction, an EMF will be induced in the rotor. Now, this is the EMF that is basically responsible for the flow of current in the rotor's winding. And obviously, since this field current and this EMF is provided by means of magnetic induction, so these machines are known as induction machines. Now, what happens that when a current flows in the rotor circuitry, it produces another magnetic field which is represented by Br, that is the rotor's magnetic field. Now obviously this rotor's magnetic field is stationary while the stator's magnetic field is rotating with a constant synchronous speed. So what happens that the rotor's magnetic field tries to catch up with the stator's magnetic field, and in an effort to be aligned with the stator's magnetic field, the rotor and its magnetic field start rotating. So eventually, what is the conclusion of all this procedure? That when the rotor gets started, eventually it approaches a speed which is quite near to the synchronous speed. Why I am saying quite near to the synchronous speed, not the synchronous speed, because what happens that as the rotor approaches the synchronous speed, now the stator's magnetic field that is rotating at synchronous speed and the rotor that is also rotating at synchronous speed. So the relative motion between the two things becomes zero. And due to this zero relative motion, EMF induced in the rotor's winding becomes zero, and hence magnetic field of the rotor becomes zero. And in this situation, rotor feels a drag force on it and it slows down. So it never reaches the synchronous speed for a longer duration. So the conclusion of this discussion is that in an induction motor, stator's magnetic field rotate with synchronous speed. Rotor's magnetic field rotates with synchronous speed, while the rotor rotates at a speed just below the synchronous speed. That is the reason that induction motors are sometimes called as asynchronous machines. Why? Because the mechanical speed of rotor is just below the synchronous speed. So since it is not synchronized with the electrical frequency, so we say that induction machines or induction motors are asynchronous machines. So this is all about the starting of this induction motor. Why? Because the starting of induction motor depends upon magnetic induction. At the start, suppose we have plugged in the switch of an induction motor at time t equals to 0. Then just after the closure of the switch, that is at time t equals to 0 plus, we can see that the relative motion is maximum. Why? Because stator's magnetic field is rotating at synchronous speed while the rotor is stationary. So at the very start of the motor, the relative motion is maximum. But when the rotor's speed, when the rotor achieves a speed near to the synchronous speed, what happens that the relative motion becomes nearly zero. So in induction machines, relative motion is quite important. So what they do, that to explain this relative motion, inshallah, we will introduce two parameters later on to make this concept more clear and understandable, that how it works for induction motors. So just now coming to the construction of induction motor. On the basis of construction, induction motors can be divided into two types. Number one, the squirrel cage induction motor, and number two, the wound rotor induction motor. So these are the two types that we use in induction motors. If we compare the two types, the squirrel cage motor is the most widely used motor of induction type, while wound rotor induction motor is not most widely used motor, but it is the most flexible motor that we use as an induction motor. Number two, squirrel cage motor is inexpensive, while wound rotor induction motor is expensive because it needs uh, a dedicated three-phase winding for the rotor circuitry. Number three, squirrel cage induction motor has a fixed EMF, fixed field current, and uh, it works for a nearly fixed load. In comparison to this, wound rotor induction motor can work at variable speed and it can produce variable torque and it can work at variable field currents. So this is a small uh, comparison between the two types of the motor. Now coming to the construction of the squirrel cage motor. In figure 7.1, you can see this cage. This is basically the rotor of the squirrel cage induction motor, and you can observe that what is happening there, that there are series of conductors. For example, first conductor, second conductor, third conductor, and similarly the fourth conductor. So these are the series of conductors that are basically short-circuited at both ends by two short-circuiting rings. This is the first short-circuiting ring, this one. So this is the first short-circuiting ring. And on the other side, this is the second short-circuiting ring, this one. So what happens that series of conductors are basically inserted in some slots. Both ends of the conductors are short-circuited by two short-circuiting rings. So overall, uh, the system resembles a cage that was uh, used earlier in some movies where they used to display that a squirrel is being basically running on this cage. So that is the reason that this motor was named as squirrel cage induction motor. So why they are integrating the conductors in series? Because the voltage builds up in series. So what will happen that all the EMFs that will be induced in these conductors will be sum up to give a more bigger or reasonable overall EMF. But the disadvantage of this construction is that when we have finished with this squirrel cage, we can't add any further conductors in it. So once this machine has been designed or manufactured, it offers a fixed EMF and it can operate for a fixed load. But this scheme is most inexpensive scheme because it is used as substitute of the three-phase winding. So obviously three-phase winding is much expensive as compared to this cage system. So therefore, yeah, we know that squirrel cage induction motors work for fixed load. They have fixed EMF built at the rotor circuitry, therefore the field current and hence the torque produced at the shaft of the motor is fixed. Still, these motors are the most widely used induction motors because they are much inexpensive as compared to the wound rotor induction motor scheme. Now coming to the second type of motor that is known as the wound rotor induction motor. So what happens in a wound rotor induction motor, that we provide the stator as the stator of the cage induction motor with a three-phase set of winding, because to the stator we have to provide three-phase set of voltages for the production of rotational magnetic field. So the stator is the same as the stator of the squirrel cage induction motor, but in the rotor circuit, wound rotor induction motor has a dedicated three-phase winding, another dedicated three-phase winding other than the stator's three-phase winding. So we can say that in wound rotor induction motors, we have two three-phase windings. One three-phase winding is installed at the stator, and the other three-phase winding is installed at the rotor. Now, the three-phase winding that is being installed at the rotor is often of the Y type. That is this type, Y. So if there are three windings for a three-phase system, then three ends, obviously three windings would have six ends. So three of one end of each winding is basically shorted at this central Y point here. So there are three ends that are knotted, joined together at this Y end, and the remaining three ends are basically, each end is connected to one of the slip rings. For example, first end is connected to this first short circuiting ring. The second end is connected to this short circuiting ring, and similarly the third end of the third winding will be connected with this short circuiting ring. So I'm sure that you have uh, worked on this three-phase induction motor in your lab. So if you can bring the motor outside of the workbench and then you open the back panel of the motor, then you can easily observe that there will be three slip rings available along with a carbon brush, along with obviously one carbon brush for each of the slip rings. So what happens that in this way they made it possible that the rotor is rotating, and still we don't have to obviously basically the rotor starts rotating. The carbon brushes are riding at one carbon brush is riding at one of the slip rings, and hence we avoid the mingling or the mixing of the wires, and hence any breakages. Na? So this is the same phenomena as I explained you for the slip rings and carbon brushes scheme for the provision of DC field current to synchronous motors. So what happens that now in the rotor winding, we have three terminals where we can connect. These are the three terminals: the first terminal, the second terminal, and the third terminal. So these are the three terminals that are basically connected to the slip rings. So now with the help of carbon brushes and slip rings, we can insert a three-phase resistor in the rotor circuit. Now this three-phase resistor in the rotor circuit can change the field current, can change the rotor current, which is known as the field current. So it can change the field current, and hence it can change the torque speed characteristic of the motor. It can change the torque at which the motor is operating. It can change the speed at which the motor is running. So it becomes a very flexible machine. So this is the reason that three wound rotor induction motor are widely used in our industry. Why? Because in our industry, particularly in the manufacturing units of our industry, what happens that sometimes we run the machine at at a higher speed. Sometimes if we don't have enough orders for production, we run the motor at a lower speed. So we need variable speed uh, depending upon our needs of the industry. So we need flexible machines that can operate on a higher speed and then on and again they can either operate on a higher speed or they can operate it to at a moderate speed or at a lower speed. So for those types of applications where we need variable speeds, we use wound rotor induction motors. And to tell you one thing, that in our industry there are three types of motor that are used. Mostly they use three types of motors. Number one, the three-phase induction motors. Why? These three-phase induction motors are mostly used for production units where we need huge torque, where we require high efficiency. So we use three-phase induction motors there. Then comes the use of stepper motors. If we have to perform some rotational movements, some steps in our, as for example, uh, 90-degree step rotation, 180-degree step rotation, then we most often we used the stepper motors. And third is the servo motors. That is basically servo motors. Why we use servo motors? We use servo motors for control purposes. So inshallah, when you will be studying in your sixth semester, I think you will be studying the linear control system. There you will be knowing that how can we control the servo motors. So and the stepper motors. So servo motors and the stepper motors will be covered in the linear control system uh, subject. And here we are discussing basically the squirrel cage induction motors and the wound rotor induction motors. So that was something regarding the construction of the two types of induction motors. Now coming to Article 7.2. Where first of all they have given the same old formula for synchronous speed, that as in synchronous machines, again in induction machines we can calculate the synchronous speed using the same formula, that is 120 F upon P. So if a machine is having four poles and it is operating at 60 Hertz, then its speed is 120 multiplied by 60 whole divided by 4, that is 1800 revolution per minute. Okay, now coming to uh, the concept of rotor slip. Actually, the working of induction motor depends upon the relative motion. As I told you earlier that in the start, the relative motion is maximum, while when the rotor gets a speed near to the synchronous speed, the relative motion becomes almost equal to zero. So to explain this concept of relative motion, they have introduced two parameters. One is the slip speed and other is the slip. So these are the two parameters that are basically used for the explanation of relative motion, that is very vital in induction motors. So first of all, coming to the first parameter, that is slip speed. What is the slip speed? Slip speed is basically the difference between the synchronous speed and the rotor's mechanical speed. For example, when the rotor is stationary, Nm, that is the rotor's mechanical speed, is 0, while N synchronous is the speed with which stator's magnetic field is rotating. So it is the synchronous speed. So initially when the rotor is stationary, what happens that Nm is 0 and slip speed is equals to the synchronous speed. So at time t equals to 0 plus, when rotor is stationary, slip speed is maximum. Now coming to the situation when the rotor starts rotating at synchronous speed, what happens that now n slip, that is the slip speed, becomes n synchronous minus n synchronous, and hence it is 0. So we can say that the slip speed is maximum when the rotor is stationary and it is equal to the synchronous speed, while slip speed is minimum when the rotor is running at constant synchronous speed and it is 0 at that time. Now coming to the second parameter is slip. Slip is basically the ratio of slip speed with synchronous speed multiplied by 100%. So obviously, slip is basically a percentage quantity. So its maximum value is 1 and its minimum value is 0. Just like the probability, where the maximum probability could be 1 and the minimum probability could be 0. So how is it possible? Consider equation 7.4. At time t equals to 0 plus, rotor's mechanical speed is 0. So slip is n synchronous minus 0 whole divided by n synchronous. That is n synchronous whole divided by n synchronous, and that is 1 multiplied by 100%, that is 1. So maximum value of slip is 1. Now coming to the other extreme, when rotor is rotating at synchronous speed, so slip becomes n synchronous minus n synchronous whole divided by n synchronous, that is 0 divided by n synchronous, that is 0. So the minimum value of slip is 0. If we compare the two parameters that are being used for the description of relative motion, that are slip speed and slip. So in my opinion, slip is more flexible. Slip is more popular among the industrial engineers. They often talk about induction motors in terms of their slip, that at what slip that induction motor is running. And experienced engineers even can discuss the uh, performance and the efficiency of induction motors on the basis of the slip they are running, they are offering during their operation. So in my opinion, slip is more popular among the industry engineers as compared to the slip speed. So in equation 7.5, what they have given is that if you want to use the angular velocity for the calculation of slip, you can simply replace n with w synchronous and nm with wm, and the formula remains the same. Now, again, if we rearrange equation 7.4, we get equation 7.5. And if we rearrange equation 7.5, if we rearrange equation 7.4, we get equation 7.6. And if we rearrange equation 7.5, we get equation 7.7. Now, what is the significance of equation 7.6 and 7.7? If you know the slip of the induction motor, you can simply subtract it from 1 and multiply the resultant with the synchronous speed to get the rotor's mechanical speed. So it makes the calculation easier. So that is why they manipulated equation 7.4 and 7.5 to get equation 7.6 and 7.7 respectively. Now coming to the rotor's frequency problem. Actually, what happens that at the start, when the rotor is stationary, induction motor behaves just like a transformer. That is the reason that sometimes we name it like a rotating transformer. Why? Because induction motor is basically quite analogous to the transformer if the rotor is stationary. Why? Because in a transformer we have two windings, primary winding and the secondary winding. In the same manner, in induction motors we have two windings, the primary winding on the stator, the secondary winding on the rotor. So as the rotor is stationary, so the primary frequency is equal to the secondary frequency because transformer does not change the frequency. So what happens that if we apply 50 hertz at the primary side of the induction motor, we will get 50 hertz at the secondary or the rotor side of induction motor. But what happens that when the rotor starts rotating, then the relative motion becomes less and less as the speed of the rotor increases. And eventually when the rotor reaches or approaches maximum or synchronous speed, the relative motion becomes zero and the frequency at the rotor becomes zero. Therefore, the rotor frequency basically depends upon slip. At start, slip is maximum, rotor frequency is maximum. At synchronous speed, slip is zero and rotor frequency is zero. So they concluded that the rotor frequency depend upon slip. So they introduced a formula to calculate or compute the rotor frequency. It is rotor frequency equals to slip time the electrical frequency provided by the mains. So we can use equation 7.8 to compute the rotor frequency at any given slip value. Then comes another short derivation that if we put the formula for slip in place of slip here in equation 7.8. So what happened that rotor frequency will become n synchronous minus nm whole divided by n synchronous time fe. Now for n synchronous, if we put 120 f upon q in the reverse manner, in the reciprocal manner, so what will happen that fe will be cancelled out with the fe of the numerator, and finally we will have another formula for the rotor's frequency, and this formula will be applicable when we have only the synchronous speed, mechanical speed of rotation, and the number of poles of any induction motor. So these were some mathematical manipulations and equations that are related to induction motors. Now coming to the first numerical of this chapter. So again, they have given you that the terminal voltage is 208 volt. The output power of the induction motor is 10 horsepower. The motor is a 4-pole motor, so number of poles are 4. It is operating at a frequency of 60 hertz, and the type of connection being used for the three-phase connections are Y connections. And they have told us that the slip at which the rotor is at which the motor is operating is 5%. So obviously 5% means 5 upon 100, that is 0.05. So question number 1, what is the synchronous speed of this motor? So we all know from chapter 4 that the synchronous speed has the formula 120 f upon p. So we know that the frequency is 60 hertz. We know that number of poles are 4. So n synchronous is 120 f upon p. That is, it is 1800 revolution per minute. So it is quite a simple part 1. Now for part B, they are asking us to calculate the rotor speed. So we learned a bit earlier that rotor speed is equal to 1 minus slip time synchronous speed. So slip is 5%. So what we did, we used the equation 1 minus slip type synchronous speed to calculate the rotor's mechanical speed. So 1 minus 0.05 multiplied by synchronous speed is equals to the rotor speed. There, here they have made some typing mistake. And what is it? They have written 0.95 mistakenly. Actually, 0.05 should be written here. So they calculated using the correct value, but they wrote a wrong value here. So 1 minus 0.05 will give you 0.95, and you will if you will multiply 0.95 with 1800, you will surely get 1710. So the final answer is correct, but mistakenly they wrote 0.95 instead of 0.05. So you can make a correction here that this is not 0.95, it is 0.05. Why? Because slip was not 95%, slip was 5%. So in the C part, they want us to calculate the frequency of the router. So we know the formula is very simple, that router's frequency is equals to slip time, the electrical frequency provided. So it is 0.05 times 60 Hertz. So we will be getting 3 Hertz as the final router frequency at the given slip. Now they are saying that if you will use the alternate formula, you will get the same result. What was the alternate formula? Alternate formula for the calculation of router's frequency was P whole divided by 120 multiplied by slip speed. So obviously 4 divided by 120 multiplied by 1800 minus 1710 will give you the same answer. So either you can use equation 7.8 or you can use equation 7.9, but in any case you will get the same result. Now the last part of the question was to calculate the induced torque on the shaft of the motor. So we were being given that the output power provided by the shaft of the motor is 10 horsepower. So we converted this into watts by multiplying it with 746. So what happened that obviously we need omega in the denominator, that is mechanical speed in radian per second. So to convert the speed in revolution per minute into radian per second, what we do, we multiply with 2 pi by 60. So here we multiplied revolution per minute, that were 1710, with 2 pi by 60 to make it a quantity in radian per second. So now it is omega 1710, that is revolution per minute, if multiplied with 2 pi by 60 will become speed in radian per second. So now the speed is omega, that is speed in radian per second. So P out divided by omega will give us torque in Newton meter. So this is the torque at the shaft of the induction motor in Newton meter. So if you want to calculate the torque in British quantity, that is foot pound, then you can do this using this formula. So if we know speed in revolution per minute and the number of poles of induction motor, we can use this formula to convert power in horsepower and speed revolution per minute. So we can use this formula to convert to calculate the load in foot pounds. So in second calculation for power P, we will be using horsepowers, and for speed we will be using revolution per minute speed, and we will get the torque in the foot pound units. So this is the torque in the foot pound unit. Now finally coming to the last topic of today's lecture, that is the equivalent circuit of an induction motor. So as I told you earlier, as a start, we can start with the equivalent model of a single phase transformer. Why? Because as in the single phase transformer, on the primary side we were having primary resistance RP and the primary impedance, primary reactance XP. So for induction motors, the primary resistance is stator's resistance and the primary reactance or inductance is basically the inductance of the stator winding. Now, obviously, when there will be a relative motion, so there will be eddy and hysteresis losses. So for to cover eddy and hysteresis losses, we can use RC in the stator winding, and similarly when the stator will produce the rotational magnetic field, we can explain or we can represent this phenomena using the axiom of the transformer model. Now coming to the router side or the secondary side. For secondary resistance in transformer model, we were used to write RS. So in place of RS, we will use the resistance of router. So we will write it RR. And in place of XS, we will write XR because here the secondary winding is on the router. So it seems that the equivalent model of a single phase transformer works quite good for an induction motor. But one thing is not being covered here. In a transformer, there is no rotating part. So the frequency at the input is the frequency at the output. But in case of an induction motor, the rotor is rotating. It's not stationary. So if the rotor is rotating, then its frequency is not fixed, it is time varying. At the start, it would be maximum. It would be equal to the supply of the main frequency of the main supply. That is, if the mains are supplying frequency of 50 Hertz, it will be 50 Hertz. But when the router will reach a speed nearly equal to the synchronous speed, its frequency becomes 0. So to incorporate this frequency change of the router, what we will do, we will only consider the router circuit for the change. Stator circuits remains the same. So for the router circuit, what they are doing, they are saying that if we draw the circuit of router, it would be just like this. Initially, what will happen? Initially, router's voltage ER would be maximum. That is, it would be equal to ER naught. Why? Because relative motion is maximum. But when the router will approach synchronous speed, ER, that is router's voltage, will become 0. So they concluded that router's voltage ER depends upon slip. Initially, it is 1 into ER naught, that is maximum, and finally it is 0 into ER naught, that is it is minimum. So now coming to the two parameters, that is resistance of armature winding and the reactance or inductance of the armature winding. We all know that resistance is not a parameter that is depending upon the frequency. So the parameter that depends upon frequency is the inductance. Why? Because for inductance, we can write that XR equals to 2 pi f LR. So this F is obviously showing that router's inductance depend upon the frequency. So what they did, like the voltage, they wrote that router's inductance XR is depending upon slip. So it is slip time XR naught. When relative motion is maximum, router's inductance is maximum. When relative motion is minimum, router's inductance is minimum, because this inductance depends upon the frequency of the system. So what will happen, that now they basically applied KVL in this diagram, and then they made IR the subject of the equation. So IR would become equal to this thing, that is ER upon RR plus GXR. Then they have skipped one step, so I am writing it here, that what happened, that afterwards they wrote what they wrote. If it can take this text box, where is the text box? Yeah. So what they wrote here is basically ER equals to S R naught whole divided by RR plus J times S X R naught. Now what happens that if we divide this fraction, that is SR naught with S, we will get ER naught in equation 7.13. So if we are dividing the numerator SER naught with S, so we have to divide the denominator with S as well. So what happened that if RR is divided by S, we will get RR whole divided by S like this. And if we divide JXS XR naught with S, so S will be cancelled with S, so we will be left with JXR naught. That is here. So hence they got equation 7.13. Now what is the advantage of equation 7.13 over equation 7.12? The advantage is that in equation 7.12 there are two terms that are dependent on S. One is ER, which is equals to SER naught, and the other is XR, that is equals to SX naught. So in equation 7.12 we have two terms that are basically dependent on S, while in equation 7.13 we did a mathematical manipulation. We divided the numerator and the denominator with S, and hence we got an equation where only one parameter, that is RR, is dependent upon the slip. So it would be much easier to use equation 7.13 instead of equation 7.12. So they have drawn another circuit that is resembling equation 7.13. So that is this circuit. If we apply KVL upon this circuit, we will get equation 7.13. So keeping in mind equation 7.13, we have drawn a new circuit and we declared it as the rotor side of the induction motor. So the advantage, as I already told you, that in this circuit only one parameter is depending upon slips, so the calculations become much easier. So hence finally the equivalent model of an induction motor becomes like this, and you can easily see that the rotor circuit is the circuit I discussed you just before this figure, that instead of being using two parameters that are depending upon S, here only R router's resistance is depending upon S. So it gives us a bit mathematical simplified version of the equivalent model. So this is basically the final equivalent model of induction motor. So if I ask a question that draw the equivalent model of induction motor and explain each terms, and you will draw this model for induction motor, and then you will explain that what are the different parameters, such as R1 is basically the armature resistance, X1 is basically the armature reactance. Similarly, RC demonstrates the eddy and hysteresis losses. XM demonstrate the magnetization of armature windings. Then X2 is obviously the rotor's self-inductance, and R2 upon S is the rotor's self-resistance that is being dependent upon the slip of the system. So finally, uh, here comes the power flow diagram of induction motors, and we all know that we provide AC electrical power at the input side of the motor. Then obviously due to this provision of electricity, what will happen that a rotational magnetic field will be produced due to flow of current in the stator winding. So due to flow of current in the stator winding, we will face the stator copper losses. Now what will happen that an EMF will be induced in the rotor winding or in the cage of the rotor. So what will happen due to this mutual induction phenomena, due to this Faraday's law of electromagnetic induction, we will be facing the eddy and the hysteresis losses as well. So we will subtract those losses from the input side. Then obviously power is being converted uh, from the stator towards the rotor. So there will be an air gap between them. So it is P air gap. And when obviously rotor is fed with a current, so there will be copper losses or I square R losses in the rotor's winding or rotor's cage. So we will subtract the copper windings that are occurring at the rotor side, and then we will be having uh, the P converted with us, and obviously when the router will rotate, so it will face mechanical losses that are basically frictional and windage losses. So we will subtract these frictional and windage losses, and then finally, due to human error, we will subtract 1% of the full load as stray losses, and finally we will get the output power at the shaft of the induction motor. So these are some power flows that of that may be used for calculations of powers at different stages of induction motor. So one thing that I want to explain you, that in induction motor, one can think that why we are using A if uh, the motor is a squirrel cage induction motor. For wound rotor induction motor, obviously we have three-phase winding on the stator and we have three-phase winding on the rotor. So we can easily compute A. That is the turn ratio. But why we are using turn ratio if the machine is acting as a squirrel cage induction motor and it has no winding at the rotor side? So the author says that obviously this is a fact that in a squirrel cage induction motor there is no rotor's winding, but still on the basis of the ratio of rotor's voltage and the stator's voltage, that is V S upon Vp, we can define an effective A. So in that case, we will name A as effective A. Not actual A, it will not be actually present there, but it can be computed mathematically. So it will not affect the refer to primary side or refer to the secondary side situations. So it is equally applicable. This was discussed here. So finally, again, after the explanation of this, we will be having the final version of the equivalent model of an induction motor. So this is basically the end of this chapter, and we will not be pursuing it any further. So it is basically the last topic of your subject. So inshallah that you will perform good in your final exams, and wish you all good luck for your final exams and your future endeavors. And I hope that you understood what I taught you in this subject. So if you have any questions regarding today's lecture, you can ask now.
सर थोड़ा सा पेपर का बता दें अगर।
बेटा पेपर अभी बना नहीं है तो बनने के बाद बताया जा सकता है। उसमें ये हो सकता है कि अभी तो आपके पास माशाल्लाह 2 वीक्स है ना, 2 वीक्स तो आपके पास अभी हैं जिसमें आप तैयारी कर सकते हैं। तो उसमें मैं ये कहूँगा कि इंशाल्लाह मैं पेपर बनाने के बाद जो नेक्स्ट वीक आएगा ना उसमें हम एक छोटी सी मीटिंग रख लेंगे। ठीक है, सीआर को कम्युनिकेट में कर दूंगा जब पेपर में बना चुका हूँ, तो उसके बाद मैं डिस्ट्रीब्यूशन भी आपको बता दूंगा। वैसे जो टेंटेटिव डिस्ट्रीब्यूशन है वो बिल्कुल वही है जो आपके एलएमएस पर मैंने कोर्स आउटलाइन अपलोड की हुई है ना, तो उस कोर्स आउटलाइन पर आप फाइनल टर्म्स में जाएं तो 5 सवालों की डिस्ट्रीब्यूशन उन्होंने दी हुई है और उन्होंने उसमें बताया हुआ है कि CLO3 से गालिबन 2 सवाल आने हैं, CLO4 से भी 2 सवाल आने हैं और फिर बिफोर मिड जो CLO1 और 2 है उससे गालिबन 1 सवाल आने हैं। तो इस सिचुएशन में आप खुद ही ये हिसाब लगा लें कि बिफोर मिड 1 सवाल और आफ्टर मिड 4 सवाल हैं। ठीक है जी, तो उसके हिसाब से
यस सर।
एक टेंटेटिव डिस्ट्रीब्यूशन तो दी हुई है, लेकिन उसके साथ मैंने जो इजाफा किया है मैंने ये किया कि इस मशीन्स का कोर्स बहुत ज़्यादा है, तो उस पर मैंने आसानी ये की है कि मैं बिफोर मिड के पहले जब बिफोर मिड का पेपर हुआ था तो मैंने कहा था एक्सरसाइज के भी सारे सवाल शामिल हैं और थ्योरी तो सारी शामिल है ही और चैप्टर्स तो हैं ही। तो मैं आफ्टर मिड में थोड़ी सी बच्चों की आसानी के लिए अमूमन मैं ये सोचता हूँ कि मैं एक्सरसाइज के क्वेश्चंस को डिस्कार्ड करवा देता हूँ। मैं कहता हूँ कि आप एक्सरसाइज के सवाल बेशक ना भी करें, हाँ एग्जाम्पल्स और एग्जाम्पल्स के लेवल के न्यूमेरिकल आ सकते हैं, लेकिन फिर मैं डेलिबरेटली ज्यादा मुश्किल बिफोर मिड से नहीं पूछता क्योंकि बिफोर मिड से पहले मैं काफी असेसमेंट कर चुका होता हूँ। ठीक है, और आफ्टर मिड के लिए भी पॉलिसी ये है कि वो तमाम टॉपिक्स जो 100% कवर हुए हैं और जिन टॉपिक्स के न्यूमेरिकल कवर हुए हैं सिर्फ और सिर्फ उन्हीं टॉपिक्स के एक्सरसाइज न्यूमेरिकल आ सकते हैं। जिन टॉपिक्स को मैंने डेलिबरेटली कोर्स के बहुत बड़े होने की वजह से लीव किया है तो ज़ाहिर अगर वो टॉपिक नहीं हुआ तो उसका न्यूमेरिकल भी कोर्स में नहीं है। ठीक है, ये टेंटेटिव तो मैंने आपको बता ही दी है कि डिस्ट्रीब्यूशन क्या है, लेकिन ऑब्वियसली जब फाइनल पेपर बन जाएगा तो उसके बाद मैं मजीद भी आपको क्लियर बता सकूंगा। तो उसके लिए कोई बात नहीं, नेक्स्ट वीक में कोई 1 आधे घंटे का वो रख सकते हैं और उसमें ये भी हो सकता है कि अगर आपने कोई क्वेश्चन करना है, कोई चीज़ समझ नहीं आ रही तो आप पूछ सकते हैं। वैसे ऑफिशियली आज 48 आवर्स तो पूरे हो गए और आपका कोर्स भी मुकम्मल हो गया, लेकिन कोई मसला नहीं है, आप नेक्स्ट वीक भी हम एक छोटी सी मीटिंग रख के ये सारी चीज़ें इंशाल्लाह डिस्कस कर सकते हैं। ठीक है, तो आपके पेपर की डेट भी गालिबन आ गई है कि वो 1 से 8 फरवरी तक कहीं हो जाएगी। तो इस दफ़ा बिजनेस स्कूल के पेपर्स बाद में हो रहे हैं और आप लोगों के स्कूल आपके पेपर्स पहले हो रहे हैं, तो इस वजह से तैयार रहें कि अगर उन्होंने 2-4 पेपर भी ऑन कैंपस ले लिए तो जैसे लास्ट टाइम यही हुआ था ना बिजनेस स्कूल के साथ कि उधर से स्टार्ट हुआ था तो उनके 2-4 पेपर ऑन कैंपस हो गए थे, उसके बाद बाकी ऑनलाइन हुए थे। तो अब आपके कम से कम 2-4 पेपर तो मुझे भी नजर आ रहा है कि वो ऑन कैंपस हो जाएंगे क्योंकि स्टार्ट वो आपसे कर रहे हैं। ठीक है जी, सही हो गया। तो इनशाला आपसे पेपर बनाने के बाद कोई एक छोटी सी मीटिंग रख लेते हैं। तो टिल देन टेक केयर एंड अल्लाह हाफिज जी। मिड का अभी तक कुछ नहीं आया था बेटा, अगर आप मिड का पूछ रहे
यस सर।
वो मुझे लगता है कि शायद उन्होंने, अगर आप मिड टर्म पॉलिसी देखें ना तो उसमें लिखा हुआ था कि अगर कोई बच्चा अपना पेपर सबमिट नहीं करा सका तो ये उसकी जिम्मेदारी होगी। ये एक सेंटेंस मिड टर्म की पॉलिसी में मैंने बाद में पढ़ा है, तो मुझे लगता है कि वो इस क्लॉज का फ़ायदा उठाते हुए शायद मिड टर्म दोबारा करवाने में इंटरेस्टेड नहीं है, वरना अब तक कुछ ना कुछ तो आ ही चुका होता। तो
सर
आप फिक्र ना करें, आप देखिए फाइनल पे तवज्जो दें। क्यों? देखिए फाइनल के सॉलिड मार्क्स हैं 50, मिड टर्म के सॉलिड मार्क्स हैं 12, तो 12 मार्क्स के लिए अपने 50 मार्क्स क्यों खराब करते हैं? आप फोकस करें फाइनल पर, फाइनल का पेपर अच्छा तैयार करें, उसमें अगर आप 50 में से 40-45 ले लेते हैं आपका अच्छा ग्रेड आ जाएगा इंशाल्लाह।
सर
ठीक है,
फाइनल में फिर मिड की पोर्शन से कुछ क्वेश्चन होंगे?
बिल्कुल, वो मैंने बताया ना कि एक सवाल जो टेंटेटिव आपकी जरा गौर से पढ़िएगा ना, जो मैंने आपको वो दी हुई है आपके पास जो है ना LMS में मैंने अपलोड की हुई है कोर्स आउटलाइन, उसमें फाइनल के पेपर की डिस्ट्रीब्यूशन नीचे दी हुई होती है। तो जो मुझे याद पड़ता है कि जो आफ्टर मिड की 2 CLOs हैं उनसे 4 सवाल हैं और बिफोर मिड की 2 CLOs से सिर्फ 1 सवाल है। तो ज्यादातर चांस तो यही है कि 4+1 आपका इस तरह से बनेगा। ठीक है,
ठीक है।
ठीक है जी। और बाकी फर्दर डिटेल्स के लिए मैंने कहा कि नेक्स्ट वीक कोई आधे घंटे की हम मीटिंग रख लेंगे अगर आपको ज़्यादा ज़रूरत पड़ेगी तो। ठीक है, ठीक है जी।
ओके
तो अब बस आज क्योंकि आप लोगों के साथ आखिरी दिन था तो बस मैंने यही कहना था कि अच्छा अच्छा पढ़ें और कोशिश करें कि जितना आप ज़्यादा से ज़्यादा इस यूनिवर्सिटी में रह के सीख सकते हैं वो आपको फ़ायदा होगा। और अगर ड्यूरिंग, क्योंकि 2 सेमेस्टर्स मैंने आपको पढ़ाया है, तो अगर ड्यूरिंग माय टीचिंग मैंने कुछ आपको ऐसी बात कह दी हो जो आपको नागवार गुजरी हो तो उसके लिए मैं माज़रत चाहता हूँ, क्योंकि ज़िंदगी मुख्तसर है, इसका कोई पता नहीं है। तो कोशिश यही करनी चाहिए कि किसी की दिल आज़ारी ना हो। लेकिन होता यही है कि टीचर अगर कभी डांट भी देता है गुस्से में तो उसका मकसद आपकी इस्लाह होता है, उसका मकसद ये नहीं होता कि वो आपको कोई बुरा समझता है। मकसद ये होता है कि टीचर ये चाह रहे होते हैं कि आप में एक बेहतरी आ जाए। तो उम्मीद यही है कि आप किसी चीज़ को नेगेटिव नहीं लेंगे और इंशाल्लाह आपका जो ये सफ़र इस यूनिवर्सिटी में चल रहा है वो अच्छा चलेगा। और आई होप कि जब आप ग्रेजुएट होते हैं तो वो आप जो है अपने लिए और अपनी फैमिली के लिए और हमारे मुल्क के लिए अच्छे ग्रेजुएट साबित होते हैं। ठीक है जी। तो अब मेरी तरफ से अल्लाह हाफिज़ और इंशाल्लाह जो है फिर अब देखते हैं कि किसी और सब्जेक्ट में, मुझे लगता तो नहीं है कि आपसे अब होगा क्योंकि मैं इसके बाद ज़्यादा पढ़ाता नहीं हूँ सब्जेक्ट। तो देखें फिर अब आपसे मुलाकात इसमें होती है या फिर बाद में होती है। ठीक है जी। तो टिल देन टेक केयर, अल्लाह हाफिज़।
अल्लाह हाफिज़ सर।